So visiting us today, we have Adam Lidz from the University of Pennsylvania, where he is a professor. Adam got his PhD at Columbia University. He was then a postdoctoral fellow at the Harvard Center for Astrophysics. And then from there, he moved on to Penn, where he's been for just under 10 years. Adam is an expert in a variety of cosmological topics, several of which he's going to tell us about today. So, take us away.
Okay, thanks a lot, Patrick, and thanks for having me out here. It's great to be here, and it's nice to be in a civilized country for once. So I'm going to tell you a little bit about cosmic reionization, and the first part of the talk is going to be about recent data. I'm going to talk about the Lyman-alpha forest, and then I will talk a little bit about the recent claim of a detection by the EDGES experiment in the globally average 21 centimeter signal. And then I'm kind of going to turn to the future and think about the prospects for studying spatial fluctuations in the 21 centimeter emission, and in particular the prospects for combining those with line intensity mapping observations and other lines. So as I was thinking about this talk, I realized that I have a lot of overlap with people here in these topics, and I feel a little bit like I'm carrying the coals to Newcastle in this talk, but nevertheless, I'll do my best. So let's start out our story with the Planck CMB map. So this radiation was released 400,000 years after the Big Bang, and the temperature scale here is showing us that the fluctuations in the temperature are only at the level of about 1 part in 10 to the 5. This is kind of our second deepest map of the universe, more or less. This is the Hubble Ultra Deep Field. Corresponds to a patch on the sky about yay big, okay? And the galaxies shown here are at a range of different distances. The most distant ones emitted their light when the universe was only about 400, 500 million years old. But the main thing to be struck by is the difference between the deepest picture we have of the universe, the CMB. The universe was smooth and simple at early times. Our second deepest picture, the universe is already complex and clumpy. So broadly, we want to try to fill in the missing pieces between the CMB and this second deepest map of the universe. So there's a more or less unexplored era between when the universe was about 400,000 years old and about 1 billion years after the Big Bang. There are galaxies that we've detected out to when the universe was only a few hundred million years old, but the statistics are pretty spotty before about 1 billion years after the Big Bang. And we think that something particularly interesting happened during this era. We think the first stars, galaxies, and accreting black holes formed at some point. Exactly when, we're not sure, but perhaps a few hundred million years after the Big Bang. And these early sources would have dramatically impacted the gas around them. They emitted ultraviolet light, which started to photoionize neutral hydrogen around them. So these colored regions in this schematic diagram are showing ionized regions forming around the first luminous sources. These ionized regions gradually grew and filled more and more volume of the universe until at some point, essentially the entire volume of the universe was filled by ionized gas, and this process is what we call reionization. And this kind of marks the transition from the simple initial conditions that we see in the cosmic microwave background to the more complex and clumpy universe that we see already in the fields like the Hubble Ultra Deep Field. So what are the main questions that we want to know? We want to know when the universe was reionized. And by that, I can be a little bit more precise. So we think that the intergalactic gas during the epoch of reionization would have resembled a two-phase medium with a highly ionized phase and a mostly neutral phase. And so what we'd like to know is what fraction of the volume of the universe was in the ionized phase as a function of time or redshift. We want to know how this happened, and by this I mean basically what was the structure of the reionization process like. How large were these ionized regions at different stages of the reionization process? But really, these two questions are kind of tools for learning who did this. So what were the properties of the first ionizing sources like? Were star-forming galaxies the dominant producers of ionizing photons? Did accreting black holes play a significant role? What were the properties of the early galaxy populations? And these questions are then connected with a whole slew of assorted other questions that we might get some insight into by studying the very first luminous sources. So how did this process affect subsequent galaxy formation? What was the typical minimum mass of a dark matter halo that could host a galaxy as a function of time? So by heating the gas during reionization and injecting it with metals, this changed the formation of subsequent galaxies. And so at some level, understanding reionization is kind of a prerequisite for understanding subsequent galaxy formation. Did quasars contribute significantly to the process? How about exotic metal-free stars? What were the escape fraction of ionizing photons from these high redshift galaxies? What was the star formation efficiency like as a function of halo mass? What were the properties of the interstellar media like in these high redshift galaxies? What was the initial mass function for star formation? And how did we form supermassive black holes that weigh as much as 10 to the 9 solar masses after only 700 million years after the Big Bang? Is there any sort of delay in structure formation that we might expect if the properties of the dark matter are such that the dark matter is warm or fuzzy, which I'll talk a little bit about later in the talk? There's a lot of real estate at high redshift, a lot of cosmological volume. And so there's a possibility that we will see some surprise. Maybe we can find some crack in the annoyingly successful lambda CDM model by studying the universe at high redshift. What are the properties of the intergalactic medium as a function of time and redshift? What is its temperature, metallicity? What are the abundance and properties of sinks of ionizing photons? What was the nature of structure formation really like at these early times? We think that helium would be doubly ionized significantly after hydrogen is reionized. But when exactly did that happen? How did it happen? And who did it? So that's the kind of intro. Now let me turn to some of the existing data. I first want to talk about observations of the Lyman-alpha forest. So a common claim, a claim that you will see in most talks about reionization is that observations of the Lyman-alpha forest tell us that reionization completed sometime above redshift 6. So in the first part of my talk, I will argue that this might not be correct and that it overlooks a possibility that might be imminently testable with existing data. So here's kind of a famous diagram from Zhao Yifan of quasars discovered. This was back in 2006 with the Sloan's Digital Sky Survey. The highest redshift quasar known at the time was at redshift 6.42. Here's its spectrum. So you see Lyman-alpha, a cutoff in the spectrum, blue-words of Lyman-alpha. And what this is coming from is photons that are blue-word of Lyman-alpha redshift as they propagate to us, and if they pass into the Lyman-alpha line along the way, they can be absorbed by neutral hydrogen that's around. And then these are quasars at lower redshifts. This one is at 5.71. And if I were to look at absorbing gas at a fixed redshift of redshift 5, that would be a vertical line here. Redshift 6 absorption I can only see in the quasars above redshift 6 up here. But you can, that would be a vertical line around here. And what you can see already just by this plot is that there's kind of some low-level transmission through the forest, typically below redshift 6, but above redshift 6, the forest is completely absorbed. A more quantitative version of that plot, made back in 2007 by George Becker and collaborators, shows the optical depth in the Lyman-alpha line as a function of redshift. The points measured towards Z of 6 quasars are shown by individual circles here, with each circle be an estimate over a 50 co-moving megaparsec of spectrum. And you can see that the optical depth is very high in those spectra above redshift 6, with some regions showing complete absorption, these upper limits. So e to the minus tau in some sense is the observable. So e to the minus 4 here is a pretty small number. So what does this mean for the ionization state of the gas in the intergalactic medium? Well, it helps to recall the Gunn-Peterson formula for the optical depth in the Lyman-alpha line. If I take a fully neutral gas parcel at the cosmic mean density at redshift 6, the optical depth is several times 10 to the 5. Okay? So the first thing that you can see is that if the neutral fraction is larger than about 10 to the minus 4, accounting for the fact that a lot of the volume of the universe is underdense, I'm going to have complete absorption in the Lyman-alpha line. So the first thing is that when the forest is completely absorbed, which is redshift around 6, we can't tell how neutral it is. If it was neutral fraction of order unity, that would be completely opaque. If it's neutral fraction of order 10 to the minus 4, that will also be completely opaque. That part is fine. What's also often claimed is that below redshift 6 or so, when we see some low-level transmission, it's often claimed that this implies that reionization definitely completed by redshift less than 6. And that sort of seems reasonable when you look at this equation. So if I want, tau, even accounting for underdense regions of the universe, to be enough to give some transmission, then I should have this be some small number like 10 to the minus 5. But I think it's not quite right. And what it misses is that reionization will be quite inhomogeneous. And this is a model of what the universe might look like when 10% of the volume is actually in the neutral phase, right? So if the universe was uniformly ionized, then 10% neutral fraction would be incredibly opaque in the Lyman-alpha line. But suppose that when it's 10% neutral by volume, there are actually highly ionized regions around that have neutral fractions of 10 to the minus 5. Then there could still be significantly neutral regions left over, and you will get some transmission through the forest in the 10 to the minus 5 regions. So you could have reionization, you could have transmission even before reionization really completes, even before these order unity neutral regions have disappeared, right? And if you account for that, then maybe reionization didn't complete until later, redshift 5 or 5.5. It's only redshift lower than 5 or so that there are almost no fully dark regions in the forest. So maybe some of these fully dark regions are actually sourced by significantly neutral islands of leftover gas. And the thing about this is that this possibility is actually pretty testable. So above redshift 6, where the forest is completely absorbed, it's hard to get much out of the Lyman-alpha forest. And so instead, when people say that the forest tells us that reionization completes at redshift 6, which you sometimes hear, they claim that this evolution in the optical depth is very rapid. But that's kind of a loose argument. My claim is that if it ends late, this is super testable. So just to show this a little bit more, at redshift 5.5, there actually are some regions that show extended, fully absorbed portions of the Lyman-alpha forest to the sensitivity that we can see. So regions that are tens, this region, this is below redshift 5.5. This is a super absorbed region that's more than 50 co-moving megaparsec across. So in the conventional, if the conventional view is right, you need to have 50 co-moving megaparsec where the gas is mostly ionized, but nevertheless just neutral enough to be opaque. But maybe this 50 megaparsec is in part sourced by some of these leftover neutral regions with order unity neutral fraction. When I first started thinking about this, I was actually thinking that this was kind of just a loophole in the analysis of the Lyman-alpha forest. I started thinking about this back in 2007, so a while ago. But I thought, oh, reionization finishes some earlier or higher redshift, and this is just a loophole that we have to close off. But now I'm actually starting to believe that this is what's really going on, and that there are these significantly neutral regions left over, as late as redshift 5.5. And one of the things that has changed is that we have new data, new quasar spectra. And this shows a particularly impressive dark gap found by George Becker, centered around redshift 5.7. It's 110 co-moving megaparsec, just completely absorbed in the Lyman-alpha forest. Okay, this is a long stretch of the universe to be completely absorbed. So the data is getting better. Here's a new version of the Zhao Fan plot showing some spectra from Eilers and Hanawi's group. And again, you see kind of part of this is sensitivity variations, but you see significant variations in the forest with different sight lines. Some of them showing significant transmission spikes, and others showing sort of complete absorption around this redshift 5.5. So the conventional view is that this sightline to sightline scatter in the transmission through the forest across tens of co-moving megaparsec is the result of fluctuations in the post-reionization IGM. I think the reionization of the intergalactic medium completed at some earlier time above redshift 6. There are none of these significantly neutral regions left over with order unity neutral fractions. But what's going on is that the radiation field after reionization fluctuates significantly. And the temperature of the intergalactic medium fluctuates significantly. And the spatial fluctuations that we're seeing are sourced by fluctuations in some combination of the ultraviolet radiation background and the temperature of the gas, with different groups kind of having different preferences for whether it's mostly sourced by UV background fluctuations or temperature fluctuations. Exactly how large the UV fluctuations are depends on what the mean free path to the ionizing photons are after reionization. So if the mean free path is larger, then each place in the IGM will see more sources of radiation, and you'll get a smoother radiation field. It also depends on how rare the sources are. If they're quasars, you can get larger fluctuations than if they're star-forming galaxies. But I think what we're starting to see now, as more data becomes available, that none of these models really does a perfect job at explaining the scatter that's observed. So people are trying to compare this to either a fluctuating UV background dominated by rare quasars in this study, or temperature fluctuations. Both models produce better agreement with the observations, but neither kind of fully captures the observed scatter in the IGM opacity. Okay. So the more radical possibility, I would say, is that reionization is actually incomplete at redshift 5.5. So sometimes this is discounted by an argument based on Lyman beta part of a quasar spectrum. If you look at the same part of the same redshift range as in both Lyman-alpha and the Lyman beta region of the quasar spectrum, you see that places where Lyman-alpha is completely absorbed show some transmission spikes in Lyman beta. And so certainly these transmission spikes are regions that are significantly ionized. Those are regions that are neutral enough to be completely opaque in Lyman-alpha. But because Lyman beta has a lower absorption cross-section, the same regions show some transmission in Lyman beta. But if you look at the spectrum, there are clearly plenty of fully absorbed regions in Lyman beta, at least given the sensitivity. So maybe these regions are partly sourced by these neutral islands, significantly neutral regions left over. And there is a recent nice paper by Laura and collaborators that shows a detailed late reionization model where they have these leftover significantly neutral regions lasting even a little bit below redshift 5.5. So wouldn't it be nice to be able to distinguish this possibility that there are these leftover neutral islands from the alternative that the gas is just completely ionized, filled with ionized gas like this later stage in their model. In this case where reionization is in fact incomplete at these late times. And the main thing here is not so much the difference between whether it is completed at 5.5 or 6. I don't really care about delta Z of 0.5, okay? But what I want is to be able to have strong evidence that we're really seeing neutral, whether the process is completed or not. Okay, one other fact I will bring in, which is there was another interesting observation recently, which is to look at that extended trough and use a narrowband selection technique to look for Lyman-alpha emitting galaxies centered around the dark absorption trough in the Lyman-alpha forest. And what they find is that there's a very prominent deficit of galaxies. This is projected distribution of Lyman-alpha emitting galaxies as a function of distance centered around that trough at 5.7. And so they see a pretty pronounced deficit. This is only from a single sight line, okay? But if you want to attribute this deficit to the fluctuating ultraviolet radiation field and explain the sightline to sightline scatter and the transmission, you need a very short ionizing photon mean free path. If there are actually these neutral islands around, they would help attenuate the Lyman-alpha and produce such a deficit. Okay, so we've been thinking about ways of testing the possibility that there are actually these neutral islands left over in the Lyman-alpha forest, even when there's some transmission through other regions. So what I'm talking about is only applicable at kind of redshifts between 5 and 6. Above 6, where the forest is fully absorbed, I can't do much. Okay, so we think we've come up with some fairly distinctive signatures that are markers for there really being significantly neutral gas left over. And to do this, basically what we're doing is shooting sight lines through a simulation of reionization and producing mock quasar spectra and looking at their statistical properties. So to explain the tests that I want to talk about, I just want to remind you of one thing about the Lyman-alpha absorption profile, which describes how the absorption is spread out over frequency space. So first there's a Doppler core set by the temperature of the gas. And then there are these wings, damping wings, that occur because of the natural line width and the fact that the n = 2 state of hydrogen has some finite lifetime. And so because of a Heisenberg delta E delta T is order h bar, that spreads out the absorption over frequency space. And the key point is that the probability of having absorption in the wing is much, much smaller than the probability of being absorbed in the core, but it's very extended in frequency space. So we will use this as sort of a test. So we have 3 tests. The first one is most model dependent. I'm not going to say more about it. And it's kind of obvious. The neutral island should result in larger dark absorption gaps than possible when the entire volume of the universe is filled with ionized gas. And it's partly going to help that there are these wings, because that spreads out the absorption over a broad range of wavelengths. The second test that we will try is to look at the fully absorbed regions. And we will try to stack different regions of many different quasar spectra around the fully absorbed regions and look at how one recovers to transmission. And the idea is that if and only if some of the saturated regions are really significantly neutral rather than mostly ionized, there should be a slow recovery to transmission because of the damping wing in the line. If the gas is highly ionized, there'll be negligible probability of absorption in the damping wing. So basically, this damping wing is a feature that has optical depth of unity when the gas is significantly neutral. But if it's highly ionized, then there's negligible optical depth in the damping wing. So it gives us a kind of marker for neutral islands. And the third test is sort of most exotic but least practical. Okay. The third test is that if there, and I'll explain this, if there are saturated regions that contain significantly neutral hydrogen, there should be a feature in deuterium Lyman beta absorption, a tiny feature just blueward of saturated regions in the Lyman beta forest. Okay, so here's an idealized case in work led by a former graduate student of mine, Matt Malloy, where we considered we put isolated, significantly neutral regions in our Mach spectra. And we just stacked the Mach spectra, knowing exactly where the edge of these neutral regions are. And again, I've now inverted this profile so that I'm looking at an absorption line. And basically, the red case is highly ionized gas, and then you quickly recover to the mean transmission, where if you have a long, significantly neutral region, you get this gradual recovery to transmission. So this gradual recovery is the feature that we'll look at. There are a lot of complications to actually applying the stacking around real data, which I'll show in a minute. But let me first explain this deuterium absorption idea. So it's kind of a happy coincidence that if I take a significantly neutral gas at redshift 6, the Lyman-alpha optical depth is a few times 10 to the 5. Cosmologically, deuterium over hydrogen has an abundance of a few times 10 to the minus 5. So that means that if I have significantly neutral gas, I should have deuterium Lyman-alpha absorption with optical depth of 10. Okay, a few times 10 to the minus 5 times a few times 10 to the 5 is about 10. That idea itself doesn't work because the deuterium absorption is shifted by only 82 kilometer per second due to the different reduced mass of deuterium from that in Lyman-alpha, okay? And therefore, deuterium Lyman-alpha would always be in the fully absorbed part of the wing. So you would never see this extra feature in Lyman-alpha. But it turns out that Lyman beta, because of the wimpier oscillator strength of the Lyman beta line, has a much wimpier damping wing. It's only about 25 kilometer per second in scale. And therefore, there should be an extra feature in deuterium Lyman beta. And that feature should have an optical depth of order 1 if you have fully neutral gas. If it were ionized at only 1 part in 10 to the 5 or neutral, then it would have negligible optical depth. So again, it's a feature with optical depth 1 if you have significantly neutral gas around. And it would occur 82 kilometer per second blueward of fully absorbed regions in Lyman beta, but not redward of such regions. So the symmetry makes kind of a nice way of testing it. So here's again a toy scenario where we just put in neutral regions into Mach spectra, where we knew the exact boundaries, and we saw that we would see this slight excess feature blueward but not redward of the saturated regions in the Lyman beta forest. Okay. So those were the ideas that we had. Now we turn to the more difficult task of actually applying this to real data. And the tricky thing basically is that suppose there's some mixture of these significantly neutral regions, but most of the universe is ionized. You still get some significantly absorbed parts in both Lyman-alpha and Lyman-beta. And what you don't want to do is dilute your stack by including too many of the ionized regions. So what we tried to do is find only regions that had extended Lyman-beta absorption, which at least in the Mach spectra are the most likely to be sourced in part by neutral gas, and look at what their Lyman-alpha opacity is like. So here's kind of a very preliminary thing of what we got. The green shows the actual spectra in 2 different redshift bins. The magenta is what we have if the universe the model if the universe was totally ionized. If we had significantly neutral regions left over, we're expecting to see this gradual wing-like recovery. We're not seeing any evidence for that. So at some level, I kind of pushed this and brought you up, hopefully to get excited about this possibility of looking for wings, but we're not seeing that in the actual data. But I'm not quite giving up yet. So we're still working on this analysis and trying to explore exactly how sensitive is to how we stack things. So I still suspect that these neutral islands might actually be there at late times. If that's true, I think we might be able to say something more direct about what exactly the neutral fraction is from the Lyman-alpha forest using essentially existing data. Okay, so I will actually now turn to say a bit about the 21 centimeter line. I'm going to start by talking about this recent EDGE's claim of a detection. So this is now a measurement of the sky averaged radio spectrum, shown here as a function of redshift for different instrumental configurations. And they claim to see this absorption feature in the spectrum that they've attributed to neutral hydrogen absorption at redshift 15 to 20. I'm quite skeptical about this claim for reasons that I could go into after the talk. But for the moment, let's take it at face value, okay? And let's think a little bit about the implications. So let me first give a very brief primer on 21 centimeter physics. So the ground state of the hydrogen atom is split by the hyperfine interaction, and the triplet state with the electron and proton spin parallel is slightly higher energy than the singlet state with the electron and proton spin antiparallel. And the energy splitting corresponds to 21 centimeter or 1420 megahertz. Quantity called the spin temperature describes the relative occupancy of the different hyperfine triplet over singlet levels. This is just the degeneracy of states factor 3. And the spin temperature is like a Boltzmann-like factor that's describing just the relative occupancy of the 2 levels. So the idea here is basically to use the CMB as a backlight. If I have a cloud of neutral hydrogen gas in between, this can imprint a feature on the CMB spectrum. I could either see an absorption feature or an emission feature. And then those photons redshift down as they propagate to us. So for example, a cloud at redshift 13, photons can interact with the cloud in the 21 centimeter line when they reach 1.4 gigahertz in the rest frame of the cloud. And then all the photons redshift down to about 100 megahertz in the case of a cloud at redshift 13. Radio astronomers describe the brightness of this in terms of temperature units with order of magnitude millikelvins. And the brightness of this cloud depends on the neutral fraction, how much neutral gas there is in the cloud, the overdensity, and this spin temperature, which sets the relative occupancy of the different hyperfine states. And a lot of the overall redshift evolution is then set by the spin temperature. So what determines the spin temperature? Well, there are three mechanisms that determine the spin temperature. First, you can have absorption or stimulated emission off of CMB photons in the Rayleigh-Jeans tail. And those tend to drive the spin temperature to the temperature of the CMB temperature. If this were the only mechanism setting the level populations, then the gas would tend to equilibrate with the CMB background. This factor would be 0, and the neutral hydrogen cloud here would be neither a net absorber nor a net emitter of CMB photons, so it would be unobservable. But there are other processes that also impact the level populations. So collisions between, mostly between hydrogen atoms, act to couple the spin temperature to the gas temperature. And if collisions are efficient and the spin temperature is coupled to the gas temperature, then you will get absorption if the spin temperature is less than the gas temperature, and emission if the spin temperature, absorption if the spin temperature is less than the CMB temperature, and emission if the spin temperature is more than the CMB temperature. And then there's a final mechanism called the Veltheisen field effect. I think you have to be Dutch to pronounce this correctly, so I'm sure I've obliterated it. But this mechanism is a little bit more subtle, and so what happens here is that if I have, imagine, for example, I have a hydrogen atom in the singlet state. So suppose I have a UV photon that comes in, it reaches the Lyman-alpha frequency in the frame of that cloud, then I can jump to the n = 2 level, one of the n = 2 level, but then I could fall back down to the triplet state. So I could go from singlet to triplet state. And remember that the decay time to go from n = 2 to n = 1 is like 10 to the minus 8 seconds. So absorption and subsequent decay of Lyman-alpha photons serves to mix the level populations. And it turns out that this acts to couple the spin temperature again to the gas temperature. So before the edges experiment, this was sort of our expectation for what the globally average 21 centimeter signal would look like. At very high redshifts, when the universe is extremely dense, collisions couple the spin temperature to the gas temperature. The gas is cooler than the CMB because it's cooling as 1 plus z squared rather than 1 plus z like the CMB. And then you would see 21 centimeter in absorption, but that collisions are only efficient at coupling the spin temperature to the gas temperature in typical parts of the universe above a redshift of 30 or so. So that fades, and we believe there would be some time when the spin temperature equilibrates with the CMB temperature, and this global signal is no longer observable. Then the first luminous sources turn on. They emit UV photons, which shift into the Lyman-alpha line, and you get this Veltheisen field effect, which again couples the spin temperature to the gas temperature. The gas temperature, we believe, is still cooler than the CMB temperature, so it's a net absorber of CMB photons. Then, lastly, as early sources of X-rays turn on, such as X-ray binaries, that will then heat the gas above the CMB temperature, which is only 30, 50 Kelvin at this redshift. And then you will see the gas in emission. All of this heating and coupling will occur much before the gas is significantly ionized, we believe. And then the signal will fade as reionization completes. Okay, so this is the cartoon, and what the edges experiment has claimed to detect is this part of the signal in absorption. But notice two things. First, if you go, my previous slide, the depth of the signal was 500 millikelvin, 0.5 Kelvin. This model, which I would expect probably an even weaker signal than shown in this model, shows 150 millikelvin. It's a factor of 3 deeper than this model, at least. So this edges experiment, if we take it at face value, which I would caution against doing, but for now, let's take it at face value. So it's surprising in several ways. First, the depth requires some mechanism to supercool the gas in order to explain this prominent absorption signal. There's another idea about an additional radio background at redshift 20, which is also hard to organize. And it requires like significant Lyman-alpha background at redshift 20 to couple the spin temperature to the gas temperature. Possible, but not easy. I'll come into it. But you also don't want any sort of heat input, okay? And in order to get the spin temperature coupled to the gas temperature, you need a bunch of early star formation to produce the UV photons that accomplish the Waldheisen field effect. But at the same time, you don't want to heat the gas, otherwise you won't get this deep trough. Then the feature also has a very surprising shape. It's flat, has like a completely flat bottom over a redshift range of about delta Z of 5. How do you do that? It seems to require some delicate balance, fine-tuning between heating and cooling. And then you need sharp evolutions on both sides of that trough. Okay. Yes, question, thanks.
So the Lyman-alpha and X-ray heating do different things, the opposite things, you're saying?
Yeah, so the Lyman-alpha photon the Lyman-alpha photons are serving to couple the spin temperature to the gas temperature. Absorption and re-emission of Lyman-alpha photons is mixing the hyperfine levels. And the level population, the temperature that describes the ratio of those populations becomes coupled to the gas temperature. Now, if there's been no heating, the gas temperature would be cooler than the CMB. But along with the early star formation, there will also be a bunch of X-rays, and those X-rays will heat the gas up. And since the CMB is only 50 Kelvin or so at these redshifts, you don't need much heating to heat the gas much above the CMB temperature.
Why doesn't the Lyman-alpha also heat up?
It turns out the Lyman-alpha photons themselves don't actually heat the gas significantly, but the full story is a little bit subtle as to why they don't heat the gas significantly. But that's a great question. So, a ton of papers was written about this from a theoretical perspective, and each of these papers sort of address one feature of the edges signal, okay? But there is actually no model, like a lot of attention was paid to ways to supercool the gas, basically. But there are no model that I know of that can actually explain all of these, especially this flat bottom, okay? This is like impossible, basically, I suppose. Anyway, motivated by that, I will just explore the implications of one aspect of the feature. If you don't believe edges, which I think there are reasons to be skeptical, which I can go into. You can just imagine maybe with a better measurement in the future, we will learn something about the onset redshift when Lyman-alpha photons first managed to couple the spin temperature to the gas temperature. So we basically tried to model what's required to couple the spin temperature to the gas temperature at redshift 20. And we made kind of a simple model where the UV emissivity is proportional to the time derivative of the halo collapse fraction above some minimum mass, where the minimum mass is basically the minimum host dark matter halo mass that can host star formation, and that there's some fraction of the halo baryons are converted into stars in such halos, and that each stellar baryon produces about 10 to the 4 photons between Lyman-alpha and the Lyman limit. So one interesting thing about that is that to get this coupling to work, you need about 1 Lyman-alpha photon for every 10 hydrogen atoms at redshift 20. And that means that there must be significant amounts of early star formation, and hence you had to have halos above some reasonable minimum mass collapsing at relatively early times. So one interesting implication of that is that it strongly constrains any model where the formation of small mass halos is suppressed. Any model with a truncation in the initial power spectrum of fluctuations, it will be hard to get such an early onset to structure formation. So in this paper, we looked at the case of fuzzy dark matter, where the dark matter has an extremely tiny mass of order 10 to the minus 22 electron volts, such that the de Broglie wavelength of the dark matter particles is enormous, kiloparsec scale. And that suppresses the formation of small mass halos. And so this is the CDM case. If the star formation efficiency is 5%, this is as a function of different minimum host mass of galaxies. And these are cases with fuzzy dark matter. This has a mass of 10 to the minus 20 eV. This is 5 times 10 to the minus 21 eV. This is a few times 10 to the minus 21 eV. And to couple the spin temperature to the gas temperature by redshift 20, you need to be above here. So basically, this model just barely does it with 5 times 10 to the minus 21 eV. This is like a really tight constraint on fuzzy dark matter. It's comparable to the tightest constraints one gets from Lyman-alpha forest. So just as that kind of a timing of first structure formation, this onset redshift is extremely powerful. The last topic that I'm going to cover in my remaining time is to say a little bit about not measurements of the global signal, but measurements of spatial fluctuations in the 21 centimeter signal. Hopefully in the next few years, we will have some detections of reionization era gas using this HERA array. And for the last few years, I've been focusing on two questions. The first is, how do we convince ourselves that an initial 21 centimeter detection is real and not residual foregrounds? Okay, so that's sort of part of the worry with the edges case, which I can talk to in the question section if you want. But the second is, how do we actually interpret what fluctuation measurement means? And for both questions, it will be really nice to be able to cross-correlate with another tracer at high redshift. Right? This would provide some smoking gun verification that we're actually seeing 21 centimeter signal from early times and not just residual foregrounds. The idea being that only the signal and not foregrounds will trace with this other, will correlate with this other tracer of high redshift structure. And ultimately, I think we want to map out the distribution of galaxies at the same early era that we get the 21 centimeter signal from. Fundamentally, reionization is about the interplay between the sources and the intergalactic gas. So if we can somehow map out the distribution of the galaxies themselves, this will be really powerful. That sounds nice, but how will you do this with what? And life is kind of hard because the 21 centimeter surveys are poorly matched to traditional galaxy surveys. So you can see this partly just by the field of view. You know, the field of view of these experiments are tens of degrees on a side. HERA will trace about 1,000 square degrees on the sky. Well, something like James Webb or ALMA has arc-minute fields of view, extremely poorly matched, like smaller than the resolution of the beam of these experiments. You might be able to do something with the hyper-supreme camera, which surveys for Lyman-alpha emitting galaxies at early times, redshift 6.6 and 7.3, and so. But even this is not easy because even the redshift interval of the narrow band is too broad. So one of the problems is that the galaxy surveys, unless you have expensive spectroscopic follow-up, are mostly measuring long wavelength line of sight modes. But those are precisely the modes that you lose in the 21 centimeter data when you clean the foregrounds. So basically, you can distinguish the foregrounds from the signal in the 21 centimeter data by using the fact that the signal in 21 centimeter has a lot of spectral structure, on the line of sight direction as I move through these ionized regions in neutral gas, there will be wild fluctuations, while the foreground, mostly galactic synchrotron, will be huge amplitude but spectrally smooth. But that means that you inevitably lose the long wavelength modes along the line of sight, the low K parallel modes. So one way to get around this is to do line intensity mapping, to give up on resolving the individual galaxies and instead observe spatial fluctuations and the collective emission from many individually unresolved galaxies in some convenient spectral line. So basically do a galaxy survey which is more like the 21 centimeter survey. And there are various lines that one can think about, rotational transitions of the carbon monoxide molecule, and people here are involved in COMAP, C+, O3, various fine structure lines. Lyman-alpha line will be targeted by SphereX, and some of these can be made more well-matched to the 21 centimeter case. The emission fluctuations in these different lines will, of course, be interesting in and of itself. And one reason that I think that's the case is that I think existing galaxy surveys are really telling us about kind of the tip of the iceberg, the bright sources that we can detect. While a bunch of the action, especially during the epoch of reionization, is coming from individually wimpy sources. And so with line intensity mapping, we can learn about the total clustered emission in different lines. So no incompleteness from sort of survey flux limits or finite aperture size. So if we could measure one of these lines, originally we were thinking of carbon monoxide for this experiment. On large scales, the galaxy emission should be anti-correlated with the 21 centimeter emission. Regions with a lot of galaxies are ionized and correspond to dim holes in the 21 centimeter map, shown here, but those would be bright regions in, for example, carbon monoxide. Showing that there is an anti-correlation could help confirm the cosmological origin of a putative 21 centimeter signal. And the cross-correlation signal depends on the size of these ionized structures. So we could learn about the size of these bubbles, which was one of the key things we wanted to learn. Okay, so this is just the correlation coefficient between 21 centimeter and carbon monoxide fluctuations, which turns over as reionization proceeds and these bubbles grow. Another thing that we'd like to learn from the 21 centimeter observations is just the overall amplitude of the power spectrum of 21 centimeter fluctuations will rise and fall with increasing redshift and neutral fraction, with the fluctuations kind of peaking around when about 50% of the volume is neutral. Recently, a number of groups have been noticing that reionization is naively a bad thing for a simple kind of biasing model, because these ionized bubbles imprint large-scale fluctuations in the 21 centimeter field. But on sufficiently large scales, like K of order 0.1, linear biasing works surprisingly well at the level of about 5%. So one thing one could try to do is just measure the redshift evolution of the linear bias factor, and that will tell us about the neutral fraction as a function of time. So recently, we in work with a very bright undergraduate student, Gus Bean, we realized that you could extract this bias factor using only cross correlations between the 21 centimeter fluctuations and 2 additional line intensity mapping data cubes. So the idea being that you could get all the information you'd like from the auto spectrum, but using only cross spectra, which would be more robust to foreground contamination. This particular ratio, the cross power between the 21 centimeter fluctuations and 2 lines divided by the cross power spectra between the lines themselves, allows you to isolate this linear bias factor in the 21 centimeter field. If you do this as a function of redshift, you can trace out the evolution of reionization as a function of time. Variants of this can be used to get rid of the foreground interloper problem that these line intensity mapping surveys will suffer from. So how do we convince ourselves the signal is real and not residual foregrounds? Cross-correlating with another tracer of high redshift structure, although not easy, seems like a powerful approach. This line intensity mapping seems like the way to go here. How do we interpret the 21 centimeter signal? The cross spectrum will turn over on the scale of these ionized bubbles. We can get at the linear bias as a function of redshift using only cross correlations with line intensity maps. So I went through quite a bit here, but I'm arriving more or less on time. So when did reionization complete? We don't know for sure, but I think there's a possibility that these neutral islands actually remain at relatively late times, and we might be able to disentangle this using existing or near future data. So far, we haven't seen any of the signatures of these neutral islands, but they still might be there. Edges is surprising if real. It's hard to explain in amplitude, shape, and onset redshift. Nevertheless, if the onset redshift is confirmed or remeasured, that's quite interesting for placing limits on dark matter models or any other scenarios with suppressed small-scale power. And finally, line intensity mapping surveys, very interesting in their own right, are promising ultimately for cross-correlating with 21 centimeter measurements during reionization. Help extract the bubble sizes in this average ionization history using only cross correlations. Thanks.
Okay, we have time for a question or two for Adam. I have a question.
Yes.
So we can find the first and third parts of your talk. Is there any hope of, if these neutral islands you were talking about exist, is there any hope of detecting 21 centimeter emission from them with something like HERAC?
Oh yeah, definitely. So the signal will be pretty small. I mean, when I say that there are these neutral islands left over, I'm talking about 10% of the volume, kind of that order. And the 21 centimeter fluctuation signal will be small when only 10% of the volume is in the neutral phase, but the detectability is much better at low redshifts than at high redshift, just mostly because the synchrotron sky is much less bright at the at those frequencies, lower redshifts. So certainly there would be a chance of seeing exactly these neutral islands in the 21 centimeter fluctuations.
Any other questions?
Yeah.
In your opinion, what's the most promising observational way that we might be able to see some of these neutral islands?
Yeah, so the thing that seems most direct to me is looking for this damping wing feature. And this is something that, I think we might see in existing quasar spectra. I mean, we've tried it, okay? We've used only a small sample of the data that's possibly available at the moment, just because it was what we had our hands on. And I think if we push on it, we might see such a signature. That, in my mind, would be the most direct marker that I can think of.
All right, well, let's thank Adam again.